we are working on non-smooth functions, and in the last class we defined a proximal operator. And proximal operator was defined as argmin x prime in Rd, and then g of x prime plus x prime minus x. So this is called a proximal operator of G. So we have seen this in the last class, and we had some results on this. So one of the results that we did in the very last class is that it's a non-expansive operator. Non-expansive operator. And this means that the proximal of G of y minus prox G of x is less than or equal to norm of y minus x. So basically this means that it's one ellipsis. Okay. So this we proved in the last class, and we will continue from there. So then we have lemma 8.17, and this says that f from Rd to R be convex and differentiable, and let G from Rd to R union plus infinity be proper LSC, lower semi-continuous, convex if x star is in the argmin of f plus g, then for all gamma greater than 0 prox lambda g, or this is gamma g x star minus gamma grad f x star is equal to x star. This is the result we have. F is convex, differentiable, and G is lower semi-continuous and convex also. So if x star minimizes f plus g, then we have that proximal of gamma g computed at this, which is x star minus gamma grad of x star. That should be x star. So let us try to convince this by proving this. So since x star belongs to argmin f plus g, from the subdifferential property what we know is that x star is the minimizer of f plus g, and f is differentiable, but g is not necessarily differentiable, but it's convex. So for g we have to use subdifferential, and for f, since it's differentiable, it's the actual gradient, and we will look at x star. So this means that 0 must belong to, so 0 must be one of the subgradient of grad f x star plus differential of subdifferential of g at x star. Okay, this is what we know. If x star is the minimizer, then we must achieve a 0 gradient vector, although there may be many gradients because of this guy, but 0 must be one of them. Okay, so this we have seen. This is Fermat's theorem, right? So okay, and yeah, basically we have to go until here. So we have to show that the proximal. So we may want to compute the proximal, We are also supposed to get the gamma here. So we will try to introduce scale g by gamma. Okay. So multiplying both, we can multiply both sides by gamma. That's right. In this inclusion, and then we are also supposed to add x star. So if we multiply by gamma on both, so gamma 0 belongs to gamma grad f plus subdifferential gamma g. It's fine. We get that, but we also have x star, so we will also add maybe x star. So we multiply both sides by gamma first and then add x star. Okay. So multiplying by gamma and adding x star. So this is also a property that we know that we are allowed to multiply. Okay, this is an inclusion, but still we are allowed to kind of multiply, and inclusion doesn't change. So in other words, 0 will also belong to grad lambda or lambda grad f plus subdifferential of lambda g. Okay, so 0 will still belong to that. Okay, so this implies 0 belongs to lambda grad f x star plus del, it was lambda or maybe gamma, I guess. So let us say it's gamma. Okay, so we have that, and we also thought of adding x star, because the way we see is that this is x star minus. So if we add x star, then we have that we will get x star minus gamma grad f star belongs to subdifferential of gamma g x star. So we can do that addition as a next step, let us say. So this will be x star, and then I also bring this guy here. So on the left, so this is gamma grad f x star, and this so basically I add and subtract, so maybe, so I will also subtract one x star, and this should be in the subdifferential of gamma g x star. Okay, all this algebra makes sense. I'm allowed to move it on the left and so on. You can verify all this. So we have that, and then we will use lemma 8.15, where the lemma 8.15 says, if you recall, we did this proof in the last class. So recall lemma 8.15. And this lemma says is that G from Rd to R and proper LSC convex XP in Rd, and if P is P is equal to proximal of G X if and only if P minus X is in the subdifferential of G at P, right? So P minus or X minus P is in the subdifferential G at P. So this we did in the last class. So since this is a if and only if case, so we are going to use this. In this case, in place of G we have gamma G, in place of P we have X star. Okay, and we are trying to conclude this. So that's how the proximal is coming. We have until here. So basically this whole thing is our x now, and this is our p. So what we have proved is that sum x minus p is in the subdifferential of g. In our case g is gamma g. Then we must have the other way also, because this if and only if, then we can claim this. So in our case p is x star, so then x star must be equal to proximal of, in our case g is lambda g, so x star is equal to proximal of lambda g, and in place of x we have this, which is exactly what we want here. Okay, so it's evident from here. Okay, so this completes the proof. Just applying this lemma, it completes the proof. So we proved lemma 8.17, and we will define something called Bregman divergence. So this is section 8.5, controlling the variance. And this is definition 8.18, and this is Bregman divergence. And this is defined as follows. So f from Rd to R differentiable. Then define the Bregman divergence as df, let us say y first, x, and this is fy minus fx minus grad fx y minus x. So this looks familiar, like if it's convex, then Bregman divergence is supposed to be greater than or equal to 0 and so on, right? But now we see this as a way of some kind of a measure, like divergence measure. So this is always non-negative, we know. Okay, so this is always non-negative when f is convex, so that we know. We can prove some results for Bregman divergence. Let us say lemma 8.19, and this is f from Rd to R convex differentiable, and g from Rd to R or union plus infinity proper LHC and convex. Then if we look at capital F, which is f plus g, then for all x star in argmin of f, for all x in Rd, we have this result where 0 less than equal to df x star, and this is less than equal to fx minus infimum of f. So this is the result on Bregman divergence, which says that it lies between 0 and the upper bound of this is fx minus infimum of f. Okay, so we know that if f is convex, this was already known to us, because this being greater than or equal to 0 is the condition for a first order condition for convexity, right? So that we knew already from convex analysis, and then what we wanted to know was whether there is an upper bound, and there is indeed an upper bound. So let us try to prove this, and we will need this. So proof of this. So since x star is in argmin of f, so since x star is in argmin of f, we can use the Fermat theorem. Basically it would mean that 0 would belong to the subdifferential of f. Okay, so g is still not may not be differentiable. Okay, so although f is differentiable, but g may not be So at least this implies that there exists a, so here we can use Fermat's theorem and some rule to obtain existence of eta star in the subdifferential of G at x star such that grad f x star plus eta star is 0. Okay, so that's roundabout way of saying the same thing, that 0 belongs to, so if you had to say this argument, then what we had is 0 belongs to grad f star so this what we the direct application of the Fermat's theorem would mean, but here we wrote it in a slightly different way. We are saying that there will exist a eta star and this is unique anyway, right? So here there is no point in picking, like this is exactly what you will pick, but here the fact that 0 belongs here, this is anyway fixed, so the choice of 0 will come from this guy, so there will be some eta, basically it will be negative of this, so that 0 will be there, right? So there exists a eta star here for which grad f star plus eta star is 0. Okay, so then now we use the definition of Bragman divergence and the convexity of G. So the result is on Bragman divergence. So it's natural that now let us look into Bragman divergence for x star. So first one is x, in place of y is x and in place of x is x star. So let us see what we can get for x star. So this is fy fx minus fx star minus grad f x and then x star minus x. Okay, so in place of y we have x, in place of x we have, okay, so now I see that I have x star here. In place of y I have x, in place of x I have x star. So I think this is the correct one. So in place of y I have x, in place of x I have x star. Yeah, that seems correct. Basically we have to prove that this is less than equal to capital Fx minus infimum of f, and f is convex also, right? So if f is convex, then what does this imply? So I mean Bragman is always greater than equal to 0, that's fine, but then we do see eta star and f star related. So one way you can think of is maybe introduce eta star there. Okay, and if you look at the upper bound, then infimum of f is already there, right? So this is the infimum of f. What we have to manage is this capital F, right? So in capital F we have G involved as well. So capital F is f plus. Okay, so somehow we have to bring in fx as an upper bound. Yeah, so let us see what is done then next. Convexity we can apply. I mean, okay, eta star was brought anyway. Oh, okay, interesting. So then we will use convexity of G as well. So let us do that. So eta star we will bring here, and since eta star is negative, so this becomes positive. And then eta star is a subgradient of, let us do the first step, which means that fx minus fx star and minus, which becomes plus, and this is eta star x minus x star. Now since eta star is a subgradient of G, right, and the definition of the subgradient, what does it tell us, right? So eta star being a subgradient means that like this is defined in a similar way, right? So if it has to be if a vector eta star has to be subgradient of G, then this guy should be positive. I mean, by this I mean replace f by G, and then for any x and y, in our case it will be x and x star. That subgradient in that case it will be eta star, and that should be greater than equal 0. That's how we define a subgradient, right? So we can work this out here. So if eta star is a subgradient, then so we will replace this by G, and what we want is eta star. So in place of x, I will take x star. In place of y, I will take x. Okay. So y is x and x is x star. F is G. Okay. Any vector that has to be a subgradient, then this is the qualification needed. This inequality should be satisfied. So we will. So what will it do? So we will solve for this basically. So eta star, we will replace that. So eta star x minus x star will be less than equal to gx minus gx star, and then we will add the xx. Fx plus gx is capital Fx, and gx star plus fx star, the way f is defined is addition of 2, so that would be the infimum. Okay, so this guy is less than equal to, so this makes it less than equal to, so this is fx plus fx star plus yeah, so gx minus, okay, that's interesting because here I missed, that's what I was wondering, how come. So this is like gx minus gx star. Okay, so this is less than this, and this guy plus this guy, we know it's capital F. So this is capital Fx minus this guy, and this guy is fx star, which is also infimum of f. Okay, so this is a result on the Bregman divergence. It's used, you will see this Bregman divergence used in few other places. So our plan is to cover stochastic optimization, which is the main workhorse of machine learning. Okay, so this is why you are seeing a lot of details there, because people work with this as a main workhorse. It's used in deep learning. So but so basically training all kind of neural networks. Okay, you start with this usual artificial neural networks, convolutional neural networks, recurrent neural networks, transformers. These are class of neural networks. Okay, and basically it never ends. People keep trying this new architecture. So for all of this, at the back end you need these kind of stochastic methods. Okay, and some of them are non-differentiable because the activation functions used are non-differentiable. So that's why we are also looking at non-smooth and stochastic. So today we will do non-smooth and stochastic as well. So that's what we are doing, and these are the tools that are needed. And this is like just mean problem. Okay, and then if you go to something like GANs Okay, generative model. So there we have seen min max problem, and so those are min max optimization. Here also we will need stochastic min max algorithms, and there are methods that use these kind of tools. So this more or less class of method covers optimization techniques. That's why I mean relevant to machine learning basically. Okay, not necessarily in other areas. So so we are moving towards the stochastic subgradient method. Okay, so what we have done is gradient method, gradient descent, stochastic gradient descent, and we are going to stochastic subgradient descent. So basically we are generalizing, so now it's also allowing non-smoothness, and that's why we have to work with these sub-differentials and so on. Okay, so these are usually advanced concepts. Okay, these are usually taught as a in advanced optimization course. So we are into, you can think of, we are into advanced topics already. Okay, so lemma 8.20 okay, so lemma 8.20 and we have variance transfer lemma, but for general convex case. So variance transfer so let f be sum of L max smooth and sum of convex, then for every x y in RD we have variance of grad f I x is less than or equal to 4 L max. Now we are bringing in this divergence, right? Bregman divergence we are bringing in this variance transfer. So far we have not seen this. Plus 2 variance of grad FIY. Okay, so this is the result. We will try to prove this. So we are supposed to use lemma 4.6 and the inequality norm of a square a plus b whole square is less than or equal to 2a square plus 2b square, and expected smoothness. Anyway, so let us start with this quantity itself, and then we will see how to derive the upper bound. So variance of grad fi x. Now we apply the definition of the variance, which is expectation of I mean not we are not applying the we will have this inequality here, and which is coming from the fact that we have done this in the lemma before. And so let me write down what exactly this is. So this is expectation of norm of fi grad fi So this is from the lemma. We have since we are not leaving anything, we must have proved this lemma 4.6, which was for all y in RD, variance of x is less than or equal to expectation of norm of x minus y squared. Okay, so there is this lemma. We have proved this before. So we just have to recall this, like and then variance of x is less than or equal to expectation of norm of this. So these two things we recall, and we have applied this directly here. So in our case, y is like grad fy. Okay, so we have used this lemma, and the next step is to expand this. and we will expand it in a way that we will add and subtract grad fi y, because we do see this thing here, so we will try to bring in by adding and subtracting this in the expectation, and yeah, and divergence term that we see, and the divergence will have grad fx. I believe the expectation will of grad fi will make it grad fx at some point. So we will have grad fx, and then other things like y minus x and so on. Yeah, and also fy minus fx and so on. Okay, I think those terms should we have to get rid of that because we don't see any of the fi terms and so on here. Anyway, let us proceed. So we will try to bring this term by adding and subtracting. So this is we will add and subtract, and then we will use that inequality, right? So what was that another inequality, which is norm of a plus b whole square is less than equal to 2 norm a squared plus 2 norm b squared. Okay, so I believe that we can verify this offline. So this inequality holds. So we will use that. So we will add and subtract first, and then we will also apply this. So if we do that, then we have further less than equal to, and then expectation of norm of grad fi x minus grad fi y norm squared plus, and then I have this 2 and then expectation of norm of grad fi y minus grad f y squared. So this follows from that. So we have added and subtracted fy y, and then we split it into 2, a squared b squared. So that's what we did here. And the next step, so if we look into this guy, then this guy is like random variable x minus its mean, right? Because we know that this is the expectation of this, right? We have done this many times now. So expectation of the fi grad fi is grad f, right? So what we see this as expectation of x minus mu. We will see this as a variance then, because that's the definition of variance, expectation of x minus mu whole square. So that's fine. So this will transform to variance. This we keep it for the moment, let's say. So this is equal to expectation of norm grad fi x minus grad fi y plus 2 variance of grad fi y. And we will invoke lemma 4.7 now, and lemma 4.7, the form of the lemma 4.7 was basically expected smoothness, okay, if you recall. So then the expected smoothness, the way it was, this will be less than equal to fy minus fx minus grad fx y minus x form, okay. So that's how those terms are coming that will become these Brakman divergence, okay. So the last step is apply expected smoothness, okay. So let us do this. So recall lemma 4.7, and this is that for L max smooth and sum of convex, then we have this result. We have actually used this multiple times, but we don't necessarily have to kind of memorize everything, but yeah. So grad fi y minus grad fi x squared is less than equal to fy minus fx minus grad fx y minus x. Okay, so this is L-max smooth property. We have also proved this result, and this will be directly applicable here, because this guy will be less than equal to 2 L-max of fy minus fx and so on. So 2 becomes 4. So we will have 4 L-max, and the right hand side is exactly df xy, and this we already achieved here. Okay, so hence the proof. Okay, so I can hence the proof. Okay, but direct application of this gives us the proof. Yeah, so our goal is to prove convergence of a stochastic subgradient descent method. So before we go there, we have like 2 or 3 more lemmas to prove. So for the stochastic, we will need maybe 2 more classes. So we will be done with the stochastic. Then we will go to the min max. Okay, where we will see how to train GANs, right? So those will be also kind of, we will start with deterministic min max, and then we will see also the stochastic variant. So a little bit of game theory will be needed there, because it's a min max problem. So that will happen after 2 classes. We want to rigorously finish this part first. So we are done with 8.20. Now we have definition 8.21, and this says f from Rd to R, and this for L-max smooth, and let G from Rd to R union infinity be proper LSC and convex. Let capital F be F plus G, and let us assume that the minimizer exists. Okay, so assume like it's well posed, right? So assume argmin of F is not empty. So we define the, so this is a definition, okay, of something called composite gradient noise. Okay, so define the composite gradient noise as sigma star f defined as variance of grad fi x star. I forgot something, and this is infimum over x star in argmin of f. So f itself is some sum of some L-max smooth. Okay, so these guys themselves may be sum of, so this is like sum of some fi. Okay, and we are instead of computing the full gradient of f, which will involve some of the gradient of fi, since we are looking into stochastic methods where we will compute gradients for loss of some of the samples in the data, and hence it becomes stochastic, because I am just looking at the gradient of fi. Okay, I am picking some of the gradients only, and then what we are looking at is if x star is the minimizer of capital F, then how does the x star, the gradient of fi at x star behave, right? How much they vary, right? Because if they don't vary much, okay, then perhaps I mean, what should we conclude, right? If they may not vary, but they may be constant. Okay, then also variance will be 0. So basically this is trying to see how much changes we see in each of these fi, in the gradient of these fi, because each of these individual fi's will be like that, some other f1, f2, okay, and f3, and x star is somewhere here. So what this result is trying to say is that x star, which is the minimizer of the sum of these guys, so let us say the sum of these guys is somewhere here, and this is the x star minimizer of this. But then in practice we are working with these guys because the stochastic method, so we are working with these guys. So hence we are interested in looking at what is happening to the gradient of these guys at the actual minimizer, right? So they may not be flat. This guy is flat, okay, it's supposed to be flat. I don't know if I have drawn it correctly. So here gradient will be 0, but we are looking at what is happening with this guys, okay, what is happening with this guy, okay, or this guy, okay, how are they behaving at the x star, which is supposed to be minimum of the f. Okay, so all these tools is used, and then that's how we get these estimates, right? So then we do this variance transfer and things like that. So we have defined this composite gradient noise, okay. So and this is the infimum we are taking, the least possible, because there may be many minimizer of capital F. So we are looking at the one out of all the minimizers of F that variance found in the grad Fi. Okay, so we'll try to interpret this thing. So the why when someone defines like this, obviously it's used as a tool to prove, right? But it's good to kind of sometimes relate it with what is actually happening. Okay, so let's see how this will be used. Okay, this is the gradient noise that we defined. So then we have lemma 8.22. So f from Rd to R, and sum of Lmax smooth and sum of convex, and Gb from Rd to R, and proper LSC convex. Then F is F plus G as usual, and well posed. So let us say minimizer exists. Then we have these 4 properties that we will try to prove. So the first one is evident. Sigma star F must be greater than or equal to 0. That follows from the fact that it's a variance. So so that's trivial, because variance is defined as expectation of something positive, so it's positive. And the second one is sigma star F is variance of grad Fi x star for every x star in argmin of F. I mean, this result seems to be interesting because if you see sigma star F we defined is to be variance of grad Fi x star. Okay, and we are looking at the infimum of all possible x star. But then the second point says is that sigma star is actually equal to directly the variance, not even looking at the infimum of those. It's like for every x star, sigma star is F star is equal to the variance. So that's interesting. Okay, so we will prove this. And then third one is if sigma F star is 0, then there exists x star in argmin of F such that x star in argmin of G plus Fi for all I. The converse is true if G is differentiable at x star. Okay, and the last one, fourth one, is sigma star F is less than or equal to 4 L max f x star minus infimum of f plus 2 sigma star f for all x star in argmin of f. Okay, so these are the results we are trying to prove now. The first one, as I said, is trivial. So let us do the second onwards. So proof 1 is trivial, and for 2 what we had as a definition is that it was infimum. So what we will show is that I will choose 2 different ones, 2 different x stars, and they will be the same, okay, for which the variance will be same. If I show that for any 2 arbitrary x star, then it will say that all will lead to the same variance, hence infimum can be removed. So let us assume that consider for 2, consider 2 minimizers x star and x prime in argmin of f, and then we will use expected smoothness that we just used some time ago, and use the expected smoothness of f. So if we apply the expected smoothness directly, so what we had is 1 by 2 L max expectation of norm of gradient of fi x star minus gradient of fi x prime whole square is less than equal to Bregman of x star x prime. So this is exactly the expected smoothness, right? So which we just used some time ago. 1 by 2 L max expectation of fi x star minus fi x prime is less than equal to basically fy minus fx minus grad of xy minus x, which is exactly the Bregman. And Bregman itself is less than equal to capital Fx minus infimum of, why should I say capital? I mean, it should be, yeah. So that was the result exactly. So df Bregman of this is less than equal to capital Fx, I mean capital Fx star, and but then both are minimizers, so it will be 0 basically, okay. And this guy is positive, and we have said that positive quantity is less than equal to 0, it must be 0. Each of these guys will be equal, and hence the variance will be same, okay, hence the proof. So this guy by definition, this is capital F x star minus fx prime. I believe that's the notations they also used, okay. I mean, if you want, you could have written it as one more step, like it's like this minus infimum of, so I treat this as some arbitrary x, but I know that it's a minimizer, so this like fx star minus infimum of f, and in the infimum of f I put fx prime because that's the infimum, right? So f x star minus fx prime, because x prime is minimizer of f, so I can put infimum, substitute that, but then I also know that x star is a minimizer, so both both are the minimizer, right? So both are the global minimizers, so they must be 0. So from here what we know is that this guy being positive less than equal to 0, so the only choice of this is that norm of this must be 0, right? So norm being 0 means the argument must be 0. So this implies grad f I x star is equal to grad f I x prime, and this is true for any arbitrary I, right? There's nothing, I mean this is true for all. So So if each of these are equal, then the variance that this guy will create will be same as the variance that this guy will create. Okay, so hence it must be that sigma star will be variance of x star, and this will be for all, because all are creating the same variance, because all are actually same. Okay, so hence the proof. Okay, hence the proof. Okay, you can write one more step, that the variance of this, so this implies that the variance of fi x star is equal to variance of, I mean grad fi x prime. So sigma f star you can pick to be any of them, because there is no point in minimizing, all are equal. So so second one is done. Now let us look at the third one. So the third one is sigma star f is 0, then there exists x star in argmin of f such that x star is in argmin of g plus fi, and then the converse is true if g is differentiable. So third one, sigma star is 0 is given, and then there exists an x star in argmin of f. We can also assume x star is in argmin of f, and then what we are really have to prove is that x star is in argmin of. So we can write down sigma star f equal to 0 is given. We can further assume that whenever like x star is in argmin of f. Okay, so let x star be in argmin. Then what we are supposed to prove is that x star is in argmin of so basically x star is in argmin of g plus fi. Okay, so there is a difference that so we have to prove is that x star, so claim is that x star is in argmin of f plus gi. Sorry, f is the sum of fi, right? So we have not said anything about g, so g plus fi, let us say. So f is basically g plus f, right? So if we look at f was sum of fi plus g, right? So what we are saying is that if x star is a minimizer of this, then x star is a minimizer of g plus fi. Okay, now the sum is removed, and this is happening because of this this guy is letting us make these arguments. Okay, so if the variance is 0, then conclusion on the minimizer of the sum is same as saying that this will be also the minimizer of g plus fi. So let us try to prove this to convince ourselves. So proof. So x star is in argmin of f, right? So and so from the previous item we can use this fact that sigma star f was supposed to be the infimum of ideally it was infimum, but then we said that infimum is not needed. So we said that it's variance of grad f. I think it's still maybe there. So variance of grad f x star. I mean, okay, why I'm making this a grad? This is variance of and these are fi, right? When I'm writing variance, then we have to take the stochastic. If I write f, then it's no longer stochastic. So variance of grad fi sigma f star, if x star is the argmin, then sigma f star is just the variance of this. If it is 0, the variance is 0, then we are able to claim this. Okay, so we start from here now. So if this is 0, then we know from previous item that that variance have been 0, right? So variance 0 would mean that all of these fi's will be same. Okay, grad fi at x star will be same, right? So let us see the consequence of this. So from previous item, since sigma f star equal to 0, we have v of variance of grad fi x star equal to 0, and so this is same as saying that grad fi, like this is the reverse of what we are doing, right? So this is same as saying that for any I these guys are equal. So this implies that not just equal, they will be also equal to they will be equal to the gradient itself, the full gradient, okay, because each of these grad fi are the same. So so if the variance of this grad fi are the same, then the conclusion is that is equal to grad f x star. So that makes sense or not? That makes sense, right? Because variance is like grad fi minus grad f whole square, basically expectation of that, and we are saying that this is equal to 0. So each of these will be equal, right? So if you look at here, so this is expectation of grad fi x star minus grad f star, and then this is equal to 0. So obviously this implies that each of these grad fi x star will be equal to grad f star, okay. So and x star is the minimizer, but x star being a minimizer implies that minus grad f star is in the subdifferential of g x star, okay. So this is a consequence of the fact that 0 is in the 0 is a Fermat's theorem basically. So this means that 0 is in the grad f star plus this, okay. So this is a consequence of that because x star is a minimizer, and so that's it. So and then but then each of these grad fx are equal to this grad fi. So I can make this conclusion that grad fi x star is also is in this, and then from there I can claim that x star is in argmin of g plus fi, okay. So that's the proof is more or less coming from there. So so this implies that minus grad fi x star is in the subdifferential of x star, and this implies that x star is in the argmin of g plus fi. So this was the forward implication, and if you look into the theorem, then it says that if g is differentiable, then you can make the other way claim. In other words, if x star is in this, then we can claim that sigma star f is 0, okay, if g is differentiable, okay. So we can also do that. So now let us prove the converse. So now assume that g is differentiable at x star, and since it's a reverse way, so now our given thing is x star is an argmin of g plus fi. So given x star is in argmin of g plus fi, so from there we deduce that since x star is in there, so again Fermat's theorem, so we have grad fi x star minus of grad fi x star is in the subdifferential of g at x star. Okay, so this implies minus grad fi x star is in the subdifferential of g at x star. Oh, I mean, we assume g to be differentiable now, right? So now it became gradient, right? So subdifferential changes to gradient, and then we will take expectation on both sides. So if we take expectation on both sides, then this will become grad fx. So taking expectation on both sides, we have minus grad f star is equal to grad g x star. I mean, this inclusion is the same thing as saying that minus grad fi x star is equal to grad g x star, because it's a gradient now, so it's a unique thing. So now we can say it's equal. Okay. So so what do we have, right? So what we have now is that from these two equations, right? So let us say this is A and this is my equation B. Then from A and B implies that, so grad gx star is minus grad fx star, so I substitute it here. So this implies that grad fi x star is equal to grad f x star. Okay, and this is true for all I, and hence the variance will be 0 basically, because each of these grad fi is equal to something deterministic. So there is basically no variance here. So variance of these is 0. Okay, so variance of grad fi x star is 0. Okay, and if variance of grad fi is 0, then this definitely implies that sigma star f is 0. So this is our third one, and then we look into item number 4, which is the last item in this theorem. And so the item number 4, we are supposed to prove that sigma star f is less than or equal to 4 L max f star minus infimum of f plus 2 sigma star f, right? So fourth is that. So since it's sigma star f, so let us start with sigma star f and by the definition of that, and then we will apply the lemma 8.20. So let us do the fourth one. So fourth one, it says so sigma star f is variance of grad fi x star, right? And this is a consequence of lemma 8.20, which we have proved just now. So this is 4 L max df x star xf plus 2 variance of grad fi xf star. So here we are taking x, in the lemma we are taking x equal to x star is in the argmin of capital F, and y equals to x star f in argmin of f. So with these choices of we have applied the lemma 8.20, and the second term is basically sigma star f, and this guy will be then less than or equal to, because this is upper bounded by fx star minus infimum of f, right? So we have done that before. So this is L max of fx star minus infimum of f plus 2 sigma. So we have lemma 8.22, and we have a stochastic subgradient method, but let's see the time. So maybe I will take 5 minutes to just define what is a stochastic subgradient method, right? So I can define this. So the 9th section in the notes is stochastic subgradient descent. So we can define something called yeah, so this is problem 9.1, and so this is not a definition, it's a problem. Basically we want to minimize a function which is stochastic in nature, right? So we want to minimize f from Rd to R, which writes as fx defined as expectation over d of f xi of x, where d is a distribution over R, or let us say RQ, and xi is in RQ, and f of xi is a stochastic function that goes from Rd to R. So f of xi so basically we are interested in minimizing functions of this type, where fx is defined to be expectation of some stochastic function like this, and this is stochastic because of the xi. So there is a parameter in this function xi which is coming from a distribution. So it's a stochastic optimization problem. So this is the problem we are looking at, and we will need certain assumptions for this. So I will just write down the assumptions and a stochastic subgradient method. Okay, so that's it. It will take maybe 5 minutes. So some of the assumptions that we will use. So this is 9.2 in the notes. So this is stochastic convex and G bounded. So here G will stand for the gradient. You will see some bound on the gradient will be needed, and this is like G bounded, and since we are dealing with subgradients instead of gradients, so it's good to highlight this. These are bounded subgradients. So some of the assumptions that we will use is, first of all, is convexity. So this says that for every xi in RQ, the function f xi is convex. Okay, although f xi is stochastic, what we are expecting is that for every xi, f xi remains convex. Subgradient selection. So this says that there exists a function g from Rd cross Rq to Rd such that for every xi in Rd cross Rq, g of x xi is in subdifferential of f xi x. So what this says is that for every pair x and xi, there is a existence of a gradient, okay, which is in the subdifferential of f xi x. Okay, so essentially it's saying that for every choice of x, every point in the domain, and for every choice of the stochastic parameter xi, I will be able to compute some gradient. Okay, So that's subgradient selection, and then the third one is bounded subgradients. So this says that there exists, as the name suggests, it's about bounded subgradients. So there exists g greater than 0 such that for all x in Rd, expectation of with respect to d of g x j is less than or equal to g square. So essentially what we are saying is that on average the subgradients that we are computing are bounded. Okay. So these are the assumptions we are asking for when we are going to do some stochastic optimization. Then to prove results, certain assumptions are needed always. And stochastic subgradient descent method is a simple method in itself. So it's again one line. So I will define this and then we will stop. So the algorithm is stochastic subgradient descent. Stochastic subgradient descent. So what this is that so we have the iterates xt and t coming from natural numbers, and xi, as we know, is a random variable, and this is sampled id xi t is follows some trend distribution d. Then this method is very simple. Xt plus 1 is xt minus, I believe, gamma t, and g of xt xi t. And the only difference from the stochastic gradient descent is, okay, so I will say this, but for the moment let me complete this last line term. So this is in the subdifferential of del f xi t xt. Okay. So let us interpret this. What is stochastic subgradient descent method? Okay, so stochastic subgradient descent method is a method where basically in place of the usual gradient you replace it by a subgradient. Okay, and that subgradient is also stochastic in nature. Okay, so that's what stochastic subgradient descent method means. Okay, so if I have to interpret this in the machine learning framework, then you have some loss function which is written as a let us say our usual is fi, right? And let us say our loss function is like this. For each sample I am computing some loss, and the first step is the stochastic gradient descent, right? So in a stochastic gradient descent I pick one arbitrary sample it, and then I compute the gradient for that sample it rather than computing the full gradient. Okay, at the current place xt. Okay, so this is stochastic gradient descent, where I, in place of g, I have f it xt, where f it is the random sample over which I compute the gradient. Now the only thing is, now we are going to the non-smooth domain. So meaning now our f are non-differentiable, possibly non-differentiable. So now this is the stochastic gradient descent, and we are looking at stochastic subgradient descent. So here the change is that now I don't have the gradient, so all the setup remains the same. This is also the same. I pick some it. Now how I relate it to this is exactly the xi t. Okay, so here, so basically the randomness parameter that you have here, so this is written in a very generic form, right? But so the choice of your gradient is like which of these you are going to pick. Okay. So, as an example you can think of the xi which is, so I may take xi to be coming from some uniform, and then among all the samples I equals 1 to m, xi will be some sample picked from there, but it may be a batch gradient descent as well. So, I may pick a batch size of b out of these. Okay. So, this might represent like batch size. So, what is happening here is that these FIs are non-smooth, non-differentiable. So, all the setting remains the same. So, you can, in your mind you can think of this as xit, okay, which is written abstractly here. So, the fact that you are picking a sample, that is the random process, and that is determining the stochastic gradient for you. And in place of this, now you have subdifferential. Okay. So, FIT computed at xt. So, this makes it a stochastic subgradient descent. Stochastic because I do not compute the full gradient, I pick any of these loss function IT, and which one I pick is random. So, that is the stochastic nature, and but then these guys may be non-smooth, non-differentiable. So, I will pick, and then the what subgradient descent is method is saying is that pick any one from your subdifferential, any one. Okay. It did not say which one. So, since it is non-smooth, you may have many gradients possible. So, the subgradient descent method is saying pick any one that you can, any of the gradient you are comfortable computing, just provide that and then run this algorithm. So, then there is a proof that even picking any of this subgradient, okay, because it is not smooth at this point, any of this still the method can be made to converge with proper choice of step size and so on. So, that is exactly the stochastic subgradient descent method. Okay. So, non-smoothness comes here. Okay. That is the only additional feature here. So, with this we can stop here, and we will not be able to prove. So, in the next class we will prove this stochastic subgradient descent, and then I will take maybe one more class to wrap up the stochastic part, and then we will go to min max. Okay. So, okay, that is all.